Okay. Good morning, everyone. 10:15. Might as well get started. Just a couple of things to point out on the website. So the virtual office hour will be 1 to 2 p.m. on Fridays. Again, I'm just going to, unless someone gives me a heads up ahead of time, I'm just going to tune in at 1 p.m. generally, and I won't wait very long to see if somebody pops in. But, 5-10 minutes, if nobody shows up, that's fine. But again, if you give me a heads up that you have a question, you want to get on at that time, I'll wait longer. Okay. And of course, again, we can schedule other times if you want, or, a lot of questions are handled pretty well by email. And then in accounting, as I noted, so assignment 2, I set the due date for a week from Monday. Okay. So we will finish the material you need for assignment 2 today. That means I probably, would have put the due date end of next week, like next Friday. But given the, the virtual office hour on Fridays, we'll give you a little more time after that with your questions. So we'll go to the following Monday, and we'll kind of try to keep that schedule with assignments as much as possible. Okay. And this is, I haven't put this date on the Moodle and Sakai sites yet. It's just printed here. Okay, the other thing is the solution to assignment 1 should now be visible to you. Okay, so you should be able to get a hold of that. We're going to look at that today. However, I want to do some other things. I want to finish up the other material first. So anyway, that's where we are. Anybody have any questions about the logistics here? Looking ahead, exam 1 is scheduled there. That could slip by 5 to 7 days. We're going to see kind of how we are at that point. But again, that's going to be a, do it, do it at home or wherever kind of exam. It will not take you days to do it, but you'll have plenty of time. So anyway, we'll deal with that as we get closer. All right, any questions? All good? Okay. Regarding, so back to our materials discussion where we left off last time, and we're going to finish up this material on these kind of basic ideas of radiation physics and how radiation interacts with matter, which are going to inform a lot of the other stuff that we're going to do later. So let's go from there. Does anybody have any lingering questions on the material from before? Okay. So basically, most of what we talked about last time were the 4 interactions that electromagnetic radiation has with matter. And again, these are distinct from the interactions that particulate radiation has with matter, okay? Because those are totally different behaviors because they're 2 different kinds of radiation. Okay, so Rayleigh, and the 4 that we were talking about were Rayleigh scatter, which is the basically the scatter where the path of the radiation changes direction, but it doesn't lose any energy. Okay, which is distinct from Compton scatter, which is a change of direction and a loss of energy. Okay. And then photoelectric effect, which is a complete absorption. So basically we lose the, we'll say X-ray, we lose the X-ray photon, or the EM radiation basically is lost and deposits its energy as well, ultimately usually as heat, but it kicks out an electron and it gives its energy to the electron, and then the electron goes and does one of those particulate interactions with matter, which is probably going to be heat, but it's also a potential ionization event, so that's certainly an issue. And then pair production, which only occurs at very high energies, right? Because you have to have at least the mass energy of 2 beta particles, because it's going to produce an electron and a positron out of it, which is going to be 511 keV times 2, so over 1 MeV. And we don't image at those energies, so this is one that doesn't happen in general where we're operating. So that's kind of the review of those 4. And then we're going to talk a little bit today of, I kind of glossed over this at the end, but this is going to come up more when we talk about how X-ray imaging actually works. Is that, well, X-ray imaging is based on attenuation of the X-ray beam, right? I think, this is more or less intuitive, but we're going to get into the physics and math associated with it. But of course, the idea is that we're applying an X-ray beam to our subject. It is going to pass through the subject, and we're going to detect on the other end. But the fact that we see objects on the other end is because some materials in the body are going to stop or scatter, or I guess more generally we would say attenuate the X-ray beam more than others, right? Bones are denser, so they're going to attenuate the X-ray beam more. Softer tissues less. Lungs have a lot of air, so they attenuate it even less. So those are kind of just intuitive thoughts about it, but of course there's a mathematical model basis for all of that we can follow. So, the kind of total effect of attenuation of the X-ray beam, or more generally electromagnetic radiation, is really composed of all 4 of those factors, right? And they contribute different amounts depending on the energy of the beam. Okay, and again, this is also a function of the material that you're passing through. Since we are mostly soft tissue, and soft tissue is a lot like water, okay? Those are, this is going to be the majority of the composition of the body, but these, these relative curves would be different if we were talking about bone. They'd be, not a lot different, but they would be a little bit different, or, whatever material you wanted to talk about. In any case, as we kind of pointed out, throughout the range of imaging energies, and again, that probably ought to go up to, roughly here, really, sorry, that comes up. We really should be kind of going up to 511 keV for PET. Okay. Still, over the majority of that range, the total linear attenuation is dominated by the Compton effect. Okay. And so most of the attenuation we experience will be photons that maybe should have made it to our detector given their initial paths, but didn't because they had a Compton interaction and they got scattered off in another direction. Okay. And it's really, as at the low end of this range, of which, we do, I mean, that does involve some X-ray imaging, right? And especially mammography is done at the very lowest end of this range. We do see, significant contributions from photoelectric and even some of the Rayleigh kind of scattering. Okay. So those are, a greater contribution at the low end of the scale, but certainly most X-ray is largely going to be dominated by Compton. Nuclear medicine, which is going to tend to operate up in this range, definitely dominated by Compton. So Compton is going to be the major effect, but we still kind of lump those effects into this linear attenuation coefficient. And the idea here, yes, question.
I'm muted. I'm not muted anymore.
Okay.
So are there ways to correct for some of these attenuations, or are they just like a basic physical principle that you can't?
Right. So that's a really good question. So, it turns out that for X-ray imaging, this is the point, right? I mean, we don't like having the scatters, okay? But I make a distinction between the scatters you don't detect and the scatters you do detect, okay? So the point of X-ray imaging, and the only reason we have contrast between different tissues in X-ray imaging, is because they have different attenuation coefficients. Okay, so we are actually imaging this effect in X-ray. Now, the fact that you have, and that's the effect of scatters that scatter but aren't detected, right? But there's also the kind of flip side of that is photons you would not have detected, but you do detect because of scatter. Okay, and generally I will tend to refer to those effects as attenuation on the one side and scatter on the other, although they're kind of both based on Compton primarily. So when we talk about detecting scatter in the image detector, then that is a problem. That does contribute trouble. And so generally in X-ray imaging, you will try to do your best to shield against that. In fact, try to stop photons that aren't traveling the right directions as best you can. You can't, it's not.
Is that with hardware or?
Yeah, very often that's hardware. So they will use, it's basically like collimating on your detector. It's a screen with with fins that are basically meant to stop photons that aren't traveling in the right direction. You can, in X-ray, you can try to use some models to try to correct for that too. Now, in PET and SPECT, attenuation is a problem, okay? Because in those, we're measuring radiation that's inside the patient and coming out. So we can't know for sure where, what direction it's coming from. But in PET and SPECT, we do have ways of correcting for this. Generally, you're going to get a map of the patient that usually is from an X-ray, from a CT, and use the map of the patient to estimate how the attenuation would apply in different locations. And we'll talk more about that with PET and SPECT. So yes, there are ways of correcting for this in nuclear medicine where it is 100% a problem, right? And they are pretty good in general, as long as you have a good map of the subject. And it is, of course, it is subject dependent. That's the thing. In the old days, they would try to use kind of a general model and make a big ellipse and use that as a kind of general way of handling it. But now we use, patient-specific image measurements to do it, and it works, quite well in general.
makes a lot more sense because everyone has different things in different places. So
Yeah, but you know, on the other hand, what that means is that pretty much all PETs are PETs combined with CTs, and a lot of SPECT systems now are SPECTs combined with CTs. So you basically bolted another imaging system onto these things. Okay. Yeah,
Thank you.
that's a good question. So the effects of X-ray attenuation, you know, if we look at it as kind of a compartment type model here or something like that, we have an incident X-ray. And again, this says X-ray, but it really is any EM radiation applies to this. Okay. It's just that I guess we most often use it in the context of X-ray, at least in the topics we're talking about. And so, you know, there is a certain incident, and I'll say a certain incident X-ray flux. And just to be clear, when we talk about flux, we're talking about photons per unit time and per unit area. Okay. So you can think of this as kind of a broad X-ray beam where all the photons are traveling in one direction, and this is very idealized, of course, because that's not really how we make them, but think of it that way anyway. And so, you know, within a certain cross-sectional area over a certain amount of time, you're going to have a certain number of photons pass through that. Okay. And so the incident X-ray flux is then, you could say, divided between two compartments. Basically, all the photons that are either absorbed or scattered off in a, let's say, hopeless direction where they would not be detected. And again, this depends a little bit on what your detector is, but let's just go with the idea. And so, you know, some number of those photons go off into that compartment, and then the remaining ones are transmitted. And it's just basically governed by an exponential equation here, where if x is kind of path length through the material, then mu is the linear attenuation coefficient, which is going to be in, let's say this is centimeters, right? Then this is going to be per centimeter, and expresses, you know, how much attenuation there is per centimeter. And so again, basically, if you travel further through the material, you're going to have more attenuation. Interestingly, this equation doesn't really go with the diagram, so I'm going to say this is n0, then this becomes n sub x. Okay. And of course, we could just subtract to get this, but we never really, for some reason, we never really worry too much about how much this is. We only worry about how much is left, right, when we get to the other side. Okay, so if we travel through more material, then because of the property of the exponential, we will have less photon flux on the other side, right? So, and again, that's intuitive, right? If you were trying to shield against X-rays, you would be pretty sure that more material would allow fewer X-rays through, and that's absolutely true. And as well, denser materials would, because denser materials will tend to have a higher mu, will also provide more attenuation, more shielding. So again, this is intuitive, and it's a pretty simple model, really, but it works. I will point out, although we're going to see a lot more of this later on the website, in the class information, the only helpful link I have, at least at the moment, and if, by the way, if you come across some helpful links, I'm glad to put them up here, is the database of X-ray attenuation coefficients compiled by the National Institute for standards and technology. And basically this gives tables of attenuation coefficients for all of the elements. Okay, and so let's say we'll just pick cobalt out of there, and come on, cobalt. We seem to be a little unresponsive. There it is. And basically it lists as a function of energy, well, it lists mu over rho, which is, I'll explain that in a second, but basically this includes mu as a function of energy. And so all of that information is there. And in fact, it also offers some of that for a select set of compounds and mixtures, some of which are bodily tissues, breast tissue, whole blood, adipose tissue, and some of which are, just materials that you encounter a lot. And again, a lot of this is driven by dosimetry. And so, a lot of this is either bodily materials, materials you might use for shielding. Some of it is materials you might find in imaging systems, things like that. Okay, and they actually have the instructions in here as well for how you could go about compiling that for some compound and mixture if you know all of its elemental content, right? So, if you had some material that wasn't listed, and I don't ever give you a problem like this, okay? But I just want you to know it could be done. If you had some material that wasn't listed, you could just go through and figure out what its mass proportions are of all of the elements, and compile its attenuation coefficient from that. Okay, so those are physical constants, and they're measured and tabulated here, and so we will make use of those later. Okay. All right. And of course, these are actually curves for water and lead, and you would find curves like these on the website. We kind of talked about that. Just to note, the mass attenuation coefficient basically is the linear attenuation coefficient divided by the density of the material. So again, the density of material X, you can look up, and it's actually in those tables for all of the things that they have. And so, and sometimes, again, this is useful for compiling mixtures of things and so forth. Or if you have a material, that, is somehow less dense than its normal state, maybe it's constructed with air pockets or something like that. You can come up with a relationship that way. But basically, all we have to do to get mu is multiply this by the density of the material. Okay. And that's a thing we will deal with later. Okay, but I just want to make make clear that there's a distinction between the mass attenuation coefficient, which thankfully is always called mu over rho. So you can tell what it is from that, and its relationship to the linear attenuation coefficient mu. Any questions on that? Okay. All right. So, as an example, let's say we have an X-ray system that's 120 kVp, which means 120 keV energy is the peak, okay? And if we consider that the fact that the patient is going to be, let's say, well, we're modeling our patient as an ellipse that's 20 centimeters this way and 25 centimeters that way. So if we say the X-rays attenuate 20% per centimeter of tissue, which is another way of saying the linear attenuation coefficient, okay, what's the intensity difference as measured by the detector in the AP and lateral positions? So basically what we're talking about is applying that mu to 20 centimeters versus 25 centimeters. And again, this is relatively simple. You don't, because we're just looking for the ratio of those two things, you don't need to know the initial flux of the X-ray, it doesn't matter. And you just apply the exponential to a path of 20 centimeters versus a path of 25 centimeters. And you find that the ratio of attenuation along those two paths is actually almost 3 times. And so as a result, you'll detect 3 times more photons in the AP, that's anterior posterior direction, than you will in the, I don't know why that's AT, but basically this is usually called right left or lateral. And so in fact, CT systems account for this now. They didn't used to, but basically they will modify the strength of the beam depending on whether it's in the thinnest part of the patient or the thickest part of the patient. And we'll discuss the reasons for that when we get to CT. But basically that's 3 times, that's actually pretty significant for that additional 5 centimeters of tissue. Okay, this does oversimplify the situation, but we'll deal with that more later. Okay. That's just kind of the basic idea of it. Sometimes, and this is more in terms of shielding, okay, people will talk about the half value layer of a material, which is directly related to its mu, okay? And the idea, of course, is the half value layer is the distance over which the beam is attenuated by a half, okay? So in other words, the photon flux decreases by a half over this thickness of material. So you could say the half value layer of aluminum at this energy, because remember this is going to be a function of energy, is whatever millimeters or centimeters. And you can derive that directly from the attenuation equation, the exponential, and basically it's going to be log 2 over mu. And in fact, this is the same math that relates the half-life in decay to the decay constant, right? Remember, those are not the same thing, but they are related. Well, half value layer and mu are related in the same way because it's the same exponential math, okay? Clearly, physically, we're talking about 2 completely different things. It's just that they use the same equations, okay? Okay, so it's important to remember, of course, that, because mu is a function of material and energy, then the half value layer is also a function of material and energy. But again, this is one of those things that's for convenience in a lot of ways. So just as, you could say the decay constant of this radionuclide is something, but it's a lot easier to talk about it in terms of half-life because you can immediately translate that, oh, it's a 6-hour half-life, so that means half of it will be gone after 6 hours. Well, if you say the half value layer of aluminum at this energy is 5 centimeters, then you immediately know what that means, right? You basically can shield half of the beam with 5 centimeters of aluminum, rather than having to say, okay, well, the attenuation coefficient is, and then I plug it into the equation. So this is, in large part a convenience for talking about these things. The measurement of these things is, it depends a little bit on how you're going to measure it. because they do talk about narrow beam and broad beam. Well, again, half value layer, but also mu, because it's kind of the same measurement, really. Because if you take on a narrow beam of the material, in other words, so you have an X-ray beam here, you collimate it so that it's a relatively narrow beam going into your material that you're measuring, and then your detector is here. Basically, if you're going to get Compton scatters, and a lot more Compton scatters are going to go off in directions that aren't detected. Okay. Whereas if you use a broad beam and don't collimate very much, then you're going to, you're going to get the direct photons, which is what you really wanted to measure here, but you're also going to get some things that, you shouldn't have detected but did. These are the things that I usually call scatter, detected scatter, that, basically would have gone off this way, except they had a Compton event and they scatter, and, again, it's a whole random distribution of angles over which those scatters can occur. Some of them are going to scatter back into your detector. Okay, so you're going to actually detect more photons here than here for the same thickness of material, and so as a result, in the broad beam case, it's going to appear to be less attenuating, right? You detected more photons than you should have detected, so it's going to appear to be less attenuating than it should have been. So the point here is it depends a little bit on how this measurement is done. Over in well, I'm pretty sure that the NIST tables are done in narrow beam geometry, but we'd have to read the introduction for that. That would be the more accurate situation. Does it make sense to everybody? This is where an example of where those scatters become a problem. Okay. And then one last item that, again, we will talk more about with X-ray. This term will come up again, but we'll bring it up here. The idea of beam hardening, the fact that an X-ray beam, as we'll see, is made up of a lot of different energies. And so, in general, because attenuation is a function of energy, it becomes actually hard to assign a single attenuation coefficient to a material when dealing with an X-ray beam, which has a lot of different energies to it. A lot of times you will kind of model and average and things like that in order to approximate those effects and simplify that process. But one aspect of that actually is the lower energy X-rays, as they pass through material and as they pass through the body, are more attenuated than the higher energy X-rays. And so as you pass through more and more material, the effective energy distribution of the X-ray beam actually changes and becomes harder, in the sense that a harder beam is higher energy on average. And so the lower energy stuff, the softer X-rays, tend to go away. And that causes some complications, especially in CT imaging, and we will, when we talk about CT, we will see that. But this is an implication of the fact that you're imaging with a whole range of energies, and the absorption and attenuation properties are different for all of that whole range of energies. Okay. Again, more about that later. So to kind of review our interactions and kind of basic issues in radiation, the radiation we're talking about is, remember, ionizing radiation is kind of where we're focusing. And so that's something with high enough energy to basically ionize an atom. And when we discuss radiation biology, we'll get into, why that's a problem. Okay. But basically, the two types in general, based on what is actually being radiated, are particles or electromagnetic. The particles, for the most part, we're interested in electrons and probably positrons also here. But again, any of the particles have these types of interactions. They may be collisional in the sense that they deposit their energy through heat and or through ionizing atoms. Okay. And they may be radiative in the sense that they actually kind of produce secondary X-rays through their interaction with materials. And again, there were two types of those: the characteristic ones, which have specific energies very specific to the material, and Bremsstrahlung, which is just a very wide array of energies. On the EM side, of course, we mentioned these, and again, it's important to be familiar with these and the differences between them, right? Rayleigh changes direction, no energy loss. Compton changes direction, there's a loss of energy. Photoelectric is absorption and a photoelectron is released. Pair production is absorption and the creation of an electron-positron pair. To note, the Compton, you might remember, it deposits, the energy loss gets deposited in an electron, right? So that's potential for an electron to get kicked out and therefore ionize. Photoelectric is potential for certainly an electron to get kicked out, potential ionization. Here you've suddenly set free an electron and a positron. Okay. Now the positrons will not last very long. That's kind of the basis of PET imaging, because they will find some electron somewhere and kind of re-annihilate themselves if this actually happens. But the electron's out there. And so, these three certainly have the potential to ionize an atom. We also have the potential for ionization here. And notice that here we have a conversion of particulate radiation to electromagnetic radiation. And in any of these where we have an electron or a particle that gets energy, basically you have the conversion the other way. Okay, and so a lot of these interactions, I guess part of the point, a lot of these interactions here generate the other kind of radiation. And it's all about balancing the energy equation, right? When they have an interaction, there is some transfer of energy from one thing to another. And sometimes, well, very often, that's producing the other kind of radiation. Okay. Any questions on that? So this kind of concludes the basics behind our interactions and things that we're going to discuss here. Is that all pretty cool? Okay. Then the thing I want to do now is look at the assignment, and that'll probably take us to finish off today. So I'm just for your information, I'm just seeing messages fly by about NC State canceling classes Monday and Tuesday because they're closing down their dorms, more or less. And again, I'm going to treat that the same way I treated UNC's announcement this week, and that is I'm still going to have class on Tuesday. And again, if you have to move or something like that, it's fine. Pick up the recording, send me questions, any of that. Hopefully that's not a problem for anybody. Okay. All right. Now, the assignment. So they're all graded and back to you. at this point, and the solution is up. And so, well, anyway, I recommend, paying attention to solutions, because sometimes I throw little nuggets in there too, right? They're sometimes worth reading. Did we have a question? Okay. All right. So, number one, this was about the full width half maximum of a Gaussian. And basically, we kind of popped through, and I think in general people got this. You can, demonstrate pretty readily this property right here, that the full width half maximum of a Gaussian is about 2.35 times sigma. And that's a thing I just remember, and a lot of people in the imaging field just remember. Okay, is 2.35 sigma. That's a kind of almost a constant that you rely on. And the point is that if you have a Gaussian curve, the full width half maximum is this distance at the halfway point. The sigma is, first of all, only one-sided, whereas full width half maximum is two-sided. And then the sigma is a little higher up, right? It's about 0.62 or something like that. So they both are measures of the width of the Gaussian, just in different places. Okay. And again, 2.35 sigma, you can rely on that, and we stick with it. The practical implication of this is that a lot of times when you're trying to, say, measure a full width half maximum in an image, okay, you will very often, even if it's not a Gaussian, the easiest way to estimate the full width half maximum of something is fit a Gaussian to the data you measure, the pixel values, fit it with a Gaussian, and then whatever sigma that Gaussian has, multiply by 2.35. This is a very common way of estimating full width half maximum, okay, by approximating with a Gaussian. Probably the most common way that it's done. Okay, so that's a practical thing, and if you're in imaging, that's going to pop up a lot probably. Part two was, okay, so this was about the ideal low pass filter, right? And so I wonder if I can write on this one. Let's see. Oh no, don't do that. Sorry. Close that. Yeah, I can't seem to write on my Acrobat reader here, so, and that's not surprising. Okay, well, but I can use my little blank space here. So the idea here, of course, is that, well, in one dimension, right, the ideal low pass filter is this thing. And, you always see this in a linear systems class, right? It's the rectangle function. And its inverse Fourier transform is the sinc function, which is sine x over x, right? Which looks like that. That's a pretty classic result from linear systems. And so the question is, okay, what if we extend this to 2 dimensions? And in which case our filter, if I basically it's all ones here and all zeros out there. This is the way I wrote it. Now you could do a circularly symmetric version of this, but I didn't do that because the math's a little harder for that one. But we're talking about, okay, what does the point spread function look like? Because that is the inverse 2D transform of this. And the kind of hand waving idea here is that, oh, okay, this function is just rectangular function in X multiplied by a rectangular function in Y. And so they are separable, which makes the math easy, because then it's really just two of these 1D inverse transforms. And so what it's going to look, well, actually, I have an illustration of that. That's probably better than I can draw in the solution. Okay, so because it's separable, you can separate the two parts of the two integrals, right? One is in X, one is in X and U, one is in Y and V, and you get the product of two sinc functions. And again, in imaging, we tend not to worry about the constants out in front because, again, you can manipulate the display contrast, and that's not really the most important part for what we're doing here. I won't say that's always true. It's just a matter of kind of having the context and understanding, okay, do the constants matter here or not? Here they don't. Honestly, we're just trying to kind of describe these things. So it's a 2D sinc function, or the separable multiplication of a sinc in X and a sinc in Y, and those would look like this if we were to display them as images, okay? And so you're going to have a peak in the middle, and then it's going to oscillate out, again, most strongly in this direction, along the cardinal directions, but some out into the quadrants as well. So a question then of that is, okay, well, what happens as you change omega naught? In other words, lower cutoff versus higher cutoff. Well, basically, you expect the point spread function as you go to a higher cutoff on that thing, you expect the point spread function to narrow, right? And most people get that because we have this kind of opposite relationship, right? And the other piece of that is, okay, we're allowing more higher frequencies through, and so it's going to have more high frequency features, which means it's going to be sharper, have smaller features. And so the size of the oscillations go down, as well as their persistence, by the way, right? How far they extend out. And so that's kind of the key thing to recognize from this. Now, as a practical matter, the oscillations are a problem. And so we never actually use filters like this because if you think about what happens at a high frequency feature, you're going to get a lot of oscillation near that high frequency feature. And so go back to my drawing space. So what's going to happen, at a kind of boundary or an edge of an image in your image is you're going to get kind of rippling effects outward from that, which it doesn't look realistic. It's a bit disturbing, and so and it also means that the effects of your smoothing are not localized. They have effects, far away from the point or the feature that you're interested in, and you generally don't want that. You want to keep, local effects local in this sense. So we generally don't use filters in imaging that have very sharp cutoffs, right? This ringing effect is a feature of the fact that filter cuts off very abruptly in the frequency domain. And so in general, we would prefer and generally use filters that have smoother cutoffs in the frequency domain, which would have more of a tendency to remove these oscillations and make them more localized. Okay. And as a result, Gaussian filters are great and probably the most often used thing. In fact, remember Gaussian frequency domain, Gaussian spatial domain, and they're nice and smooth. Of course, there's no ringing involved. So, well, and I should say approximate Gaussians, because we do get like a tiny bit of ringing in these approximate Gaussians, but for the most part, they don't produce this kind of ringing. Another alternative is the Butterworth filter, which, you know, if you had the signal processing class, you're a little bit familiar with, and in that you can actually control the rate at which the frequency space drops off, and so you can, you know, have some control over, you know, whether you get ringing or not, and suppress it if you need to. Okay, so another, you know, again, these are the things that are kind of some of the practical matters that pop up. I think most of my most of the homework problems have some link to something practical. Okay, so then we talked about a cascaded system, right? And again, everything's described by Gaussian functions because they're easy to deal with. And so, you know, if we go back to question 1 and rely on that 2.35 thing, well, basically, if we put these in the form of Gaussians, then we know what their sigmas are, and 2.35. And so we can find their full width half maximum directly from that. A lot of you just went ahead and derived it, which was fine, but was a little redundant with what we did up in number 1. So this is a fine way to do it. As some of you know from my other courses, I'm always in favor of doing things the easy way, if there is an easy way. Okay, and so in terms of a cascade now, well, we know the sigmas, so we know what the transforms are, right? We know that the sigma just flips over, and again, they're proportional. We're not going to worry. The constant in front is not going to be all that important here. And we multiply them in the frequency domain, which means we add the things in the exponents, and so we get that. And then the net frequency response is the product of, and by the way, that's another Gaussian, okay? We multiply 2 Gaussians, we get a Gaussian. We convolve 2 Gaussians. If we had done this in terms of a convolution, we get a Gaussian. This is the beauty of Gaussian functions, why we end up using them a lot, because they tend to produce more Gaussians. Then ultimately, we actually get a result that is a sigma of 2.23. And some of you got answers that were a little different from this, but I let them slide. I'm not sure why, but I did. In any case, we should get for the net system 5.22 millimeters. And again, the practical implication of this is that, oh, well, you know, that's dominated by this guy, right? It's only a little higher than this. And so the net effect, of course, is dominated by the system that's worse. The other thing is that, you know, based on this, in fact, for Gaussian point spread functions in a cascaded system, you can approximate the full, well, actually, it's exact if it's truly Gaussian, but in cascaded systems in general, you can approximate the full width half maximum of a cascaded system as this, the quadrature result of the individual full width half maxima, again, based on modeling things as a Gaussian. So, you know, you could then, as a kind of shorthand, quick way of understanding that, okay, I have this system, it's got a certain full width half maximum. I have this system, it's got a certain full width half maximum. I can at least approximate and get a rough idea of what the net result is based on this. Okay. Any questions on that one? Okay. Number 4, so there were a variety of ways to deal with that. And so I gave you some data and said, you know what? I kind of wanted you to confront the problem, the practical problem here of, okay, first of all, if I want to know the contrast of an object on a background, and especially if there's noise present, as there is here, you know, how do I define what the object is? So in general, it's going to be a, you know, not great answer to just find the maximum pixel, because that's going to be much more subject to noise. You know, if we did a different measurement of this, we might have greater noise variations, or, you know, and positive or negative in the noise, that could impact that a lot more than averaging, right? And, you know, again, intuitively, hopefully everybody understands. The reason we do averaging is to get a better estimate of the behavior and tend to average out or smooth out the noise. So if we want to, you know, really estimate the contrast of an object, we don't want to depend on just one pixel for that. We want to, you know, get an idea of the whole object. And so as a result, we need to come up with some way to define what the object is. You know, what part of the signal, in this case is just one dimension, constitutes the object. And so a way to do that, and actually a way that's often done in practice, because you don't really, you know, if you're looking at an image, you don't know exactly where the object begins and ends, is to say, okay, I know this is within the object. I'm going to take the maximum value and take some percentage of that. Might be 50%. In some applications, people have chosen 47%. Don't know why. They had some justification for doing that. But basically, you need to, you know, it's a little bit arbitrary how you choose that, but it's okay as long as you kind of stick with it, right? And always measure them the same way if you're comparing things. So in general, the way, you know, that's kind of the way it would be done. Either find the maximum and take some percentage of the maximum, or something that, you know, gives you some area. So if we averaged all that, we would get a certain value, and that would be fine. Same is true in the background, right? So we have to decide what is background. Here, it's not too hard to just kind of select these things that appear to at least kind of average out into a straight line. So we select certain things to be the background. And by the way, we're going to use the noise level, so it's a good idea to kind of pick a uniform region and get the standard deviation as an estimate of the noise. And a lot of you chose that. It's probably the most reasonable thing to do. And you probably got different results, and generally that's fine. I was just mostly looking at how you did it, but basically calculate the contrast as the subtraction between the average of this and the average of the background, and relative to the background. And then a contrast to noise ratio would be basically that over standard deviation. In some cases, you used basically the numerator of this in the contrast to noise ratio, and that would be more like signal, because contrast is generally a ratio, right? And so I made a note of that. And so a better answer is making that a contrast where it is normalized to the background. And you'll find in a lot of cases, and if you've been in my other courses, you know this is true, you know, there are many good answers, but some answers are better than others. Okay. Okay. The NEQ question, the point here is actually that the NEQ, because the NEQ of a filter, okay, affects both signal and noise the same, right, in terms of the frequencies that are attenuated, the NEQ, which is a function of frequency, actually doesn't change by passing through any linear system, with the exception of zeros, right? You know, you might get a 0 over 0 that you have to deal with, but let's kind of forget that. And so that's, you know, both good and bad. First of all, you know, you might ask the question, okay, well, if that's true, then why do we even bother filtering? Well, it's because we don't see that way, for one thing, right? We see in kind of the distribution of power in different frequency bands, and so by filtering out the high frequency bands where maybe there's more noise than signal, when we see things and kind of integrate across in certain ways across the frequency spectrum, it actually makes a difference, okay, because we're nonlinear, right? This is about linear systems don't really change the NEQ, but we're nonlinear. So that's a reason why, okay, NEQ doesn't really reflect how we see. On the other hand, it does kind of, if you can measure it for a system, it really does point you to the fundamental physics and properties of the system, limitations of the system, and any kind of downstream stuff that's linear, you know, if you think of it as a cascaded system, doesn't really affect that. And so it kind of comes back to very fundamental, but it's hard to measure too. So, you know, it's not, you know, medical physicists sometimes like to try to do that measurement, but it's not easy. It's not something you just sit down and do in a day. You really have to plan it out and do it very carefully. But it does tell you kind of the fundamental properties and fundamental trade-offs in your system between signal and noise. So there's that. That's, you know, again, the fact that it's a difficult measurement is one thing, one reason why you don't see it. It's complex, hard to report, and you don't boil it down to, you know, one number like signal noise ratio, right? So, okay. Last one, comparing these systems in terms of resolution versus noise. And again, it's partly to get used to these kinds of comparisons and having an understanding of this trade-off, which pops up all the time. And it's important to remember, right, when we're measuring resolution in terms of full width half maximum, a small value is good, right? So being closer to the origin is good. Noise variance is not too hard to see that closer to the origin is good. You could use a different, you know, measure of resolution and flip this thing over, but then all of the relationships change. So I'm always drawing it this way. The question, you know, kind of hinged on, okay, which is better and which is better in certain situations. And so, first of all, comparing system 1, solid line, and system 2 in this smaller dashed line, the line with smaller dashes, the point is that system 1 is always better than system 2 for all applications based on this, because for any given level of resolution, system 1 has lower noise than system 2. And you could look at it the other way, right? For a given level of noise, draw a straight line up, system 1 has better resolution than system 2. And because the whole curve of system 1 is closer to the origin than system 2, system 1 always beats system 2. The more complicated case, and what usually happens in practice, is the comparison of system 1 and system 3, which is, the two lines cross. And so now there's not you know, one is not always better than the other. It really depends on where your operating point is in terms of noise and or resolution as to what's the most important in your application, right? And so the point there is, if you need really good resolution and you want to operate, you know, closer to this part of the space, then system 1 is going to be better, because at these levels of resolution, it's going to have lower noise than system 2 if we kind of draw the line this way, right? And so that translates to, well, you know, if I need to see tiny little things in the image, I need really good resolution. So that task translates to this part of the space. On the other hand, if I don't need really good resolution, but I'm trying to quantify, say, large regions, and I want accurate quantification, then that might suggest operating in this part of the space where the resolution is not as important, but the noise variance certainly can affect the accuracy of quantification, right? It's going to introduce more noise and more inaccuracy, uncertainty as to what the actual value is. Then I might prefer system 3 in that case because it has lower noise at those larger levels of resolution. And so, you know, when the curves cross, then it's not an obvious answer that one is always better than the other. It might depend a lot on what it is you need to do. And that's, again, the practical implication of that. Anybody have any questions related to all that? Does that all make some sense there? Again, I try to focus on things that are have some connection to practical stuff, because these are things we're going to talk about as we kind of talk about these different systems. Okay. And we used almost all of the time today. It's good. Any last questions on anything? Going once, going twice, going 3 times. Okay. So I will be on tomorrow at 1 o'clock. I kind of don't expect people because the assignment isn't due for another week. And if I've learned anything, it's that people kind of wait till the last minute to do these things, which is fine. So, you know, I will be on, but I'm not necessarily expecting anybody. But you are certainly welcome to drop in with a question. That said, I think we will close it out for today. So thanks, everybody.
Thank you.
Nice to have you on. See you on Tuesday, if not tomorrow.